So we'll begin with two-dimensional analysis. Okay, now when we talk about two-dimensional analysis, okay, we first will see few types of elements in two-dimensional analysis, and then we will see the derivation of shape functions for three-noded triangular element, and also we will see how to find out the stresses and strains, okay, in the two-dimensional three-noded triangular element. Okay, so these are few two-dimensional elements I have drawn over here. Okay, so first element is three-noded triangular element. Okay, three-noded triangular element. So it has three nodes. Okay, now the types of elements, okay, are based on the shapes of two-dimensional geometries. Okay, now triangle is one shape. Okay, then you have rectangle is the other shape, and after that it is a quadrilateral. Okay, it is a quadrilateral. Okay, now triangle and rectangle, since they have shape conformity, okay, so what do we mean by that? Their shape will not change. Okay, so triangle will always have three sides and it will look like a triangle. Okay, similarly rectangle will also have four sides and it will look like a rectangle all the time. Okay, but when we talk about quadrilateral, okay, quadrilateral is a general four-sided figure, and it doesn't have a specific shape. Okay, it doesn't have a specific shape. Okay, so it can attain any kind of shape. Okay, and it is four sides. Okay, that is what the important thing is. Okay, so the first two types, which is three-noded triangular element and four-noded rectangular element, okay, will retain their shapes, that is triangle and rectangle, when we mesh the geometry. Okay, and if it's a triangular geometry, okay, let's say let it be triangular geometry, or say a rectangular geometry, or any other shape geometry. Okay, triangle will always try to fit in, okay, in most of the geometries, and will give us good quality mesh. Okay, rectangle, in order to use rectangular element, the geometry has to be rectangular. The geometry should have straight edges. Okay, if not probably totally rectangular, but it should have straight edges so that rectangle can fit itself in. Okay, so trying to fit a rectangular element, okay, rectangular element in a geometry is a difficult task, and it depends on what is the type of geometry, what is the nature of geometry. Okay, if it is having straight edges, then my rectangular element can fit in very well. If it is not having straight edges, then it would be difficult. Okay, now three-noded triangular element will have three nodes at its three vertices. Okay, four-noded rectangular element will have four nodes at its four vertices. We generally number the elements in the counterclockwise direction, that is starting from 1 2 3 in this way, then 1 2 3 4. Now this total is one element of say two-dimensional nature. Okay, so don't be confused that whether I have three lines. Okay, it is not a combination of three linear bar elements, or here four linear bar elements. No, it is a planar element. So the entire area that it is covering, okay, it is a filled area. Okay, it is a filled area. Okay, it will not have thickness. Okay, it will not have thickness. We have seen plane stress problems. Okay, we have seen plane stress problems, so they follow the plane stress conditions. Okay, they follow the plane stress conditions. So it's a one element. Okay, it's a one element. The nature of this element is two-dimensional. Okay, it has x dimension as well as y dimension. Okay, similarly I can add complexity. Okay, I can add complexity in triangular element. Okay, on each edge. Okay, on each edge, as I can see, there are only two elements, okay, of triangular element of triangle. Okay, so the nature of that triangular element is still linear. Okay, it is still linear. Okay, so if I add more nodes, okay, if I add more nodes, okay, so let us add one node each, okay, on the edge. So that will take us three nodes on each edge of the triangle, and that becomes six-noded triangular element. Okay, that becomes six-noded triangular element. Okay, and the nature of this six-noded triangular element is quadratic. Okay, nature of this six-noded triangular element is quadratic, because as you can see, on an edge I have 3 nodes. Okay, on an edge I have 3 nodes. When that kind of thing happens, okay, that edge can take a shape of curvature. Okay, that edge can take a shape of curvature, and that nature of curvature will always be quadratic. Okay, nature of curvature will always be quadratic, and that is the reason why I have drawn it in this way. Now, what is the benefit? The benefit is I can use such type of element in complex geometries where there are curvatures involved. Okay, where there are curvatures involved, because the element can attain a second degree curvature. Okay, element can attain a second degree curvature, or edge of element can attain second degree curvature or quadratic curvature. Okay, similarly, I have a 4-noded quadrilateral element. Now, the reason why I have drawn the shape as square shape, okay, this is square shape, this is rectangle shape. So rectangular element, when I say, okay, the shape of the element is not gonna change. Okay, but when I say quadrilateral element, okay, it is a general 4-sided geometry. Quadrilateral is a general 4-sided geometry, and that gives it a almost infinite number of shapes. Okay, that almost gives its infinite number of shapes, or let us keep it finite number. Okay, and finite number is so large that it can be fitted in any kind of geometry. Okay, that it can be fitted in any kind of geometry. And when I add extra nodes, okay, when I add extra nodes on the edges, okay, the nature of the element changes. Okay, and it becomes 8-noded quadrilateral, and the nature becomes 8-noded quadrilateral, and nature becomes quadratic in nature. So 4-noded quadrilateral is still a linear nature. Okay, because along the edge it has only 2 nodes. Okay, so the edge phenomena will be linear, so I can have slanted edges. Okay, I can have slanted edges. Okay, and I can achieve many shapes. Okay, many shapes. Okay, but when I add extra nodes, it becomes 8-noded quadrilateral element. The nature on each edge becomes quadratic, and that gives us many more different shapes. Okay, and that allows us to use this element again at intricate shape geometries where I have curvatures involved. Okay, so that was about the 2-dimensional elements. Okay, now after this we will see a 3-noded triangular element in detail. Okay, so I have drawn here 3-noded triangular element. Okay, this is my global coordinate system. Okay, this is node number 1 with coordinates x1 y1, this is node number 2 with coordinates x2 y2, and this is node number 3 with coordinate x3 y3. Okay, now on each node, okay, on each node, as the dimensions have increased, okay, from 1 dimension to 2 dimension, okay, now whatever we are seeing are all plane phenomena, okay, or plate phenomena, wherein I have a surface. Okay, I have a surface, and on that surface I am going to let's say apply certain properties and find out the various say primary variables and secondary variables. Okay, now having said that, okay, how we are going to find out the degree of freedom on each node. Okay, now when I am talking about a structural problem, okay, when I am talking about a structural problem, okay, my each node, okay, can move in x direction as well as it can move in y direction. Okay, so that gives me 2 degrees of freedoms. Okay, that gives me 2 degrees of freedoms. Those 2 degrees of freedoms are coming from the nature of element. Now, a nature of element is 2-dimensional, so it requires 2 values, okay, which are the x dimension value and y dimension value to completely define any point. Okay, to completely define any point, and that is the reason why when I say x0 y, that is the global coordinate system I am having. Okay, the coordinate of node 1 is x1 comma y1. Okay, I cannot just give the value of x1 and say that is the coordinate. Okay, that is not possible. That will not completely define the position. Okay, so in order to define the position, I should be supplying both values, that is x1 value and y1 value, and that is the same phenomena we are using to define the degree of freedom. Okay, so on each node it has 2 degrees of freedom. Okay, so along x and along y. So along x I am specifying the variable as u1, and u1 being the primary variable along x, and v1 being the primary variable along y. Okay, so on each node it has 2 degree of freedom. Okay, I have 3 nodes. Okay, I have 3 nodes in triangular element, so 2 degree of freedom on each node multiplied by total 3 nodes, that will give me 6. Okay, multiplication comes out to be 6, and that is going to be my what? That is going to be my the order of stiffness matrix. Okay, order of stiffness matrix for this element. Okay, order of stiffness matrix for this element, that is we are going to find out. Okay, so similarly u1 v1 for node 1. Okay, then u2 v2 for node 2, u3 v3 for node 3, and from u1 to v3 I have total 6 primary variables. Okay, total 6 primary variables. Now in order to continue the analysis for this 3-noded triangular element and find out the stiffness matrix of this 3-noded triangular element, okay, trying to work always with, let's say, 6 primary variables or a 6 by 6 matrix, okay, would be a headache. Okay, would be a headache. Okay, it's not even possible on a calculator to solve a 6 by 6 matrix. Okay, remember we are deriving, so we will not have values. We'll have to work with variables, and everything we have to do manually. Okay, so we will try to find out, is there any other way wherein we can reduce the complexity of the matrix size. Okay, and we have one way. So since we are saying the 3-noded triangular element will have 6 total degrees of freedom. Okay, 2 on each node, you have 3 nodes, so total 6. Okay, so on each node it has 2 degree of freedom. Okay, that is to be considered only in structural field. Okay, that is to be considered only in structural field. Okay, now we have various field problems. If we move our field problem to a thermal field, okay, now what happens is, in structural field the primary variable is displacement, and displacement is a vector quantity. Okay, so displacement is gonna change if we consider the displacement change in x, displacement change in y, so we will have different values. Okay, but when we move into the thermal field, okay, the primary variable there is temperature, and temperature being a scalar quantity, okay, it doesn't depend on dimension. So let's say if we convert this and apply this concept on a thermal field problem, okay, then on each node I will only have 1 degree of freedom, that is temperature, because temperature doesn't depend on x direction, y direction. Temperature being a scalar quantity, it spreads uniformly. Okay, so it doesn't have a direction specificness. Okay, so that property of thermal field we will use, and the degree of freedom gets reduced to 1. Okay, degree of freedom gets reduced to 1, and that is the reason why the stiffness matrix order will also somehow gets reduced to half of the previous structural field, and that becomes 3 by 3, and 3 by 3 is manageable. So what we will do, we will apply this concept to a thermal field problem, derive all the necessary matrices, the equations, and then we will extend it to a structural field problem. That is quite easy. Okay, that is quite easy. So that is why a temperature degree of freedom, the temperature is a function of x and y. Okay, a function of x and y. So we can assume an approximate function, okay, which is a linear approximate function. So c0 plus c1x plus c2y. Remember, we only want up to linear power. Okay, the reason is, okay, the nature of element is linear. Okay, nature of element is linear. It is linear 3-noded triangular element, you can also call it in that way. Okay, so in a linear approximate function, this approximate function, if we would have written for a one-dimensional field, then we would have only written c0 plus c1x. Remember how we used to write the one-dimensional approximate functions? Okay, linear if it is, then it is c0 plus c1x, which is only equation of line. Okay, which is only equation of line. Okay, if we have to write a quadratic approximate function, then it is c0 plus c1x plus c2x square. Okay, and so on. Okay, and so on. Okay, now at that time we had some other rules, okay, which we followed, okay, in order to derive the differential equation. Okay, but as far as the approximate function is concerned, okay, this still is a linear approximate function, but it is in 2 dimensions. So as you can see, x power is 1. also it will have a y power, and that y power will also be 1. Okay, so I have a linear approximate function for temperature DOF, that is T x comma y is C0 plus C1x plus C2y. Okay, now when I apply it for the element, okay, and find out the nodal temperatures, okay, so this T x comma y will be replaced by the nodal values, which are nodal temperatures, that is T1, T2, T3, and this xy will be replaced by the coordinates of at each node. So T1 will have C0 plus C1x1 plus C2y1. Okay, T2 will have C0 plus C1x2 plus C2y2, and T3 will have C0 plus C1x3 plus C3y3. Okay, that is very simple to understand. Now if I convert this into a matrix form, okay, on the left hand side I will have a column matrix T1, T2, T3, okay, is equal to, if I take out C0, C1, C2 common, okay, it will stay on the right hand side, that is again a column matrix C0, C1, C2, and in between I will have a square matrix, okay, of the kind 1 x1 y1, 1 x2 y2, 1 x3 y3. Okay, now my aim here is to find out the values of these constant parameters, that is C0, C1, C2. Okay, C0, C1, C2. Okay. Now, in order to find the values of these constant parameters, okay, I must find the values of C0, C1, C2. Okay, now in order to do that, okay, I must have C1, C2, C0, C1, C2 on the left hand side and everything on the right hand side. Since this is a matrix equation, so what we can say, I can pre-multiply both sides by inverse of this matrix. Okay, I can pre-multiply both sides by inverse of this matrix, and that eventually will give me C0, C1, C2 equal to, okay, inverse of this matrix. Okay, inverse of this matrix multiplied by T1, T2, T3. Okay, multiplied by T1, T2, T3. Now, how to find inverse of a matrix? Okay, for finding the inverse of a matrix, we'll use a known formula, that is, let's say, let us call this matrix as, A, and this becomes A inverse. Okay, so how we are going to find A inverse? It will be adjoint of A divided by determinant of A. Okay, adjoint of A divided by determinant of A. How do you find adjoint of A? Adjoint is nothing but transpose of a cofactor matrix. Okay, transpose of a cofactor matrix. So cofactor of A transpose divided by determinant of A. So here I have found out cofactor matrix transpose, okay, which comes out in this way. Okay, the cofactor matrix transpose is a matrix of coordinates. Okay, it's a coordinate matrix. Okay, so eventually it is going to be a constant. Okay, eventually it is going to be a constant. So since coordinates, we will have certain coordinates in global coordinate system. So x1, y1, x2, y2, x3, y3 are all constants, because once I give you values of x1, y1, x2, y2, x3, y3, okay, it will be only numbers. Okay, so what we are dealing here with numbers. Okay, so when eventually it will be found out, we will have some number values. Okay, for number values. So x2, y3 minus x3, y2, x3, y1 minus x1, y3, and x1, y2 minus x2, y1. Similarly, the second row is y2 minus y3, y3 minus y1, y1 minus y2, and the third row is x3 minus x2, x1 minus x3, and x2 minus x1. Okay, now since all these are very big differences, okay, equations, okay, so we will call them the first row elements we will call as alpha 1, alpha 2, alpha 3. The second row elements we will call as beta 1, beta 2, beta 3, and third row elements we will call as gamma 1, gamma 2, gamma 3. Okay, now having said that, how we are going to identify the determinant of A? So determinant of A, already know how we can find determinant of A. So determinant of A is nothing but, okay, x2 y3 minus x3 y1 minus x1 y1 minus x1 y3 plus x3 y1 minus x2 y1. Okay, we have followed the same way to find determinant. So 1, then x2 y3 minus x3 y2, then minus x1, then I have y3 minus y2, okay, and so on. Okay, and so on. That is what we have done. Okay, that is what we have done, and rearrange the terms. So if I actually try to find out what exactly is this, okay, this is also going to come out as a constant only, but this eventually comes out to be 2 times of area of that triangle. Okay, 2 times of area of that triangle. So if we know the coordinates, okay, if we know the coordinates, okay, the determinant is twice the area. Okay, determinant is twice the area of that triangle. Just to prove that, okay, I have taken here a small triangle x1 y1 x2 y2 x3 y3 with values 0 0 as x1 y1, 4 0 as x2 y2 and 2 2 as x3 y3. Okay, I will find the area of triangle. Okay, now I know that the base is of 4, okay, and height is of 2. So half base into height, the area of triangle comes out to be 4 square units. Okay, and if I find the determinant, because I know the coordinates, okay, I know the coordinates, so the determinant comes out to be 8. Okay, determinant comes out to be 8, which is 2 times of the area which we have found out. Okay, which is 2 times the area that we have found out. So it proves that the determinant of a triangle is twice multiplied by its area. Okay, twice multiplied by its area. So now, having said that, what we have got, determinant is twice the triangle area. Okay, determinant is twice the triangle area. So I have this cofactor transpose divided by area of triangle, which is 2 times. Okay, 2 times area of triangle. So I will rearrange the terms. I have C0, C1, C2 equal to 1 upon twice the area of this triangle multiplied by this alpha 1, alpha 2, alpha 3, beta 1, beta 2, beta 3, gamma 1, gamma 2, gamma 3 multiplied by the temperature nodal temperature vector. Okay, that is T1, T2, T3. Now when I solve this, okay, when I solve this, eventually what I get is alpha 1 plus beta 1 x plus gamma 1 y, okay, divided by 2 times the triangle area multiplied by T1. Okay, then plus alpha 2 plus beta 2 x plus gamma 2 y divided by 2 times the triangle area multiplied by T2, and alpha 3 plus beta 3x plus gamma 3y divided by 2 times of triangle area multiplied by T3. Now whatever there in the bracket, okay, whatever there in the bracket are my shape functions. Okay, whatever there in the bracket are my shape functions, because they are correlating what? This is my interpolation function. If you remember, okay, when we have written this, okay, this is my interpolation function and this is what we have written. Okay, eventually after finding all these values, we have put all the values back into this equation. Okay, back into this equation, and then again simplified. Okay, then again simplified, and that is why we are getting this x and y getting multiplied. Okay, x and y getting multiplied with C1 and C2. Okay, so when we arrange this eventually in my first equation, which was t which is function of x and y, okay, as a linear function, which is C0 plus C1x plus C2y. Okay, so whatever the coefficients of constants, okay, whatever are the coefficients of constants or the constant itself, okay, constant itself are nothing but my shape functions. And if you can see, tx comma y is my interpolation function. Okay, so interpolation function is shape function multiplied by primary variable. Okay, summation of shape function multiplied by primary variable. This is what we had seen in one dimensional analysis also, and this is what we derive here. So these are all my shape functions. Okay, these are all my shape functions for 3-noded triangular element. So let us look at the strain, okay, of the 3-noded triangular element. Okay, now as we have already seen, okay, we have found out the values of these shape functions n1, n2, n3, and that's what I was talking about, the interpolation function when we consider the thermal field, okay, for 3-noded triangular element. Okay, I get it in this particular form where my n1, n2, n3 are shape functions. Okay, so which are of the form 1 upon 2 times the area of triangle multiplied by alpha I plus beta ix plus gamma iy, where I varies from 1 to 3, which are the node numbers. Okay, which are the node numbers. When I subsequently applied for the structural field problem, okay, now I know that in structural field, okay, I have 2 degrees of freedom. Okay, u in x direction and v in y direction, which are my displacements. Okay, so ux comma y becomes n1 u1 plus n2 u2 plus n3 u3, and v of x comma y becomes n1 v1 plus n2 v2 plus n3 v3. Okay, now when I rewrite this into matrix form, okay, I get this kind of a matrix: n1 0, n2 0, n3 0, 0 n1, 0 n2, 0 n3. Okay, so it's a matrix 2 by 6, okay, multiplied by 6 by 1, okay, 6 by 1. So again I get 2 by 1, which is this, okay, which is this equation. Okay, so this particular matrix I'm calling it as shape function matrix multiplied by the primary variable vector matrix, which is denoted in structural field by delta. In thermal field it is denoted by temperature E, okay, TE. Now stresses and strains. Okay, now we have already seen in plane stress and plane strain problem. Okay, this particular condition is plane stress condition. Okay, so the strains I can easily find out. Okay, so epsilon x is the x directional strain. Okay, so which is given by dou u by dou x. Okay, epsilon y is given by dou v by dou y, and shearing strain in xy plane is given as dou u by dou y plus dou v by dou x. Okay, this is what we have seen in the plane stress condition as well. Okay, now when I apply this, okay, now what is u? U is basically n1 u1 plus n2 u2 plus n3 u3. Now what I have said, it is going to be a partial differential with respect to x, okay, for u. So as you can see, there is no v term present. Okay, so it is going to be partial differential of n1 with respect to x. Then the second term will remain 0, as you can see over here. Then again dou n2 by dou x, then 0, dou n3 by dou x, and 0. Okay, so that is my dou u by dou x. Okay, then second is dou v by dou I. Okay, now wherever I have 0 terms, okay, they will remain as 0. Okay, so here it will become dou n1 by dou I, then 0, then dou n2 by dou I, then 0, then dou n3 by dou I. Okay, now remember my n1, n2, n3. What are my n1, n2, n3? Okay, it is 1 divided by 2 times the area of triangle multiplied by this alpha I plus beta I x plus gamma I y. Okay, if you carefully remember, okay, what we had derived earlier, okay, this alpha, beta, gamma are all coordinate values. Okay, so it's a equation of coordinates. Okay, so it is having some equation of x2 y3 minus x3 y2 of that kind. Okay, multiplied eventually with the coordinates of the triangle. So eventually this n is nothing but constant. Okay, this n is nothing but constant, which is eventually giving us some value. Okay, eventually giving us some value. So what we are doing over here, we are partially differentiating. What we are doing, we are partially differentiating with respect to x first, then with respect to y, and then with respect to xy both. Okay, so in order to find the shearing strain in xy plane, okay, I eventually get dou n1 by dou y, then dou n1 by dou x, then dou n2 by dou y, dou n2 by dou x, and then dou n3 by dou y, dou n3 by dou x. Okay, so this is what? This is 3 rows, okay, and 6 columns. So this is a 3 by 6 matrix. This is what? This is a 3 by 6 matrix multiplied by 6 by 1. Okay, multiplied by 6 by 1. So eventually it will give me a 3 by 1. Okay, 3 by 1 matrix, which is what on the left hand side that I have got. Okay, this is a 3 rows 1 column, so this is 3 by 1, and we eventually are getting 3 by 1. So I'll just write the orders over here. Okay, the order of this is 3 by 6, and the order of this matrix is 6 by 1. Okay, so eventually when I multiply them, okay, what I will get? I will get back this strain matrix. Okay, strain column matrix. So multiplication is gonna give me epsilon x separately, epsilon y separately, and psi xy separately. That is the shearing strain. Okay, now this particular matrix is very important to us. Okay, this particular matrix is called as matrix B. Okay, multiplied by this matrix is my delta E matrix. Okay, which is the primary variable matrix. Okay, column matrix. So this B matrix is called as strain displacement relation matrix. Now why it is called as strain displacement relation matrix? On the left hand side I have strain, that is epsilon x, epsilon y, and shearing strain xy, and on the right hand side, the column matrix side, I have the primary variable. Okay, now primary variable is what? Primary variable in structural field is displacement. So this particular matrix, okay, is giving us a relationship between strain and displacement. Okay, this particular matrix is giving us a relation between strain and displacement, and that is the reason why this matrix is called as strain displacement relation matrix. It is generally denoted by capital B. Okay, it is generally denoted by capital B, and this is eventually what capital B we get. Okay, now how I have found out? Okay, if you remember from previous, okay, n1 dou n1 by dou x, dou n2 by dou x, dou n3 by dou x. Okay, now if you remember, n1 is of this kind. Okay, n1 is of this kind. When I partially try to differentiate, okay, let us take this example. Okay, when I partially differentiate this with respect to x, since it's a partial differential, okay, I will only involve terms which are having x in it. Okay, the terms which are having x in it. So there is only one term, beta I multiplied by x. Now I stands for nodal values, so that is 1, 2, 3. So it will have three values, beta 1 x, then beta 2 x, and beta 3 x for n1, n2, n3 respectively. So when I partially differentiate this, so when I partially differentiate n1 with respect to x, I will get beta 1. Okay, I will get beta 1. Remember this 1 by 2 times area, okay, being a constant value will remain outside. Okay, will remain outside. Okay, then when I will differentiate n2 with respect to x partially, I will get here beta 2. When I differentiate n3 with respect to x partially, I will get here beta 3. So that's what I have written here, beta 1 0, beta 2 0, beta 3 0. Similarly, when I try to differentiate it with respect to y, okay, I only have one y term, which is gamma I multiplied by y. So that is gamma 1 y, then gamma 2 y, then gamma 3 y for my various 3 nodes. Okay, so when I differentiate n1 with respect to y partially, I get gamma 1. When I differentiate n2 with respect to y partially, I get gamma 2, and similarly I get gamma 3 when I differentiate n3 partially with respect to y. And then I have the reverse orders. So here it will be gamma 1, beta 1, gamma 2, beta 2, gamma 3, beta 3. Now all these are what? These are coordinate values. So beta 1 being y2 minus y3, then y1 y3 minus y1, and y2 minus y1, and so on. Okay, we have found out what these betas and gammas are. So these are nothing but these. See, alpha was a multiplication and subtraction. Okay, beta and gamma are simply subtractions. Okay, simply subtractions. So this is what? This is nothing but a constant. Okay, this is nothing but coming as a constant. And in that sense, okay, in that sense, when you consider back here again the strain values, okay, these are all what? A constant multiplied by the primary variable matrix. Okay, constant multiplied by the primary variable matrix, and this is what? This is eventually strain. Okay, so that is the main reason, okay, why this particular 3-noded triangular element is also called as constant strain triangle, or in short it is called as CST. Okay, in short it is called as CST. Now why it is called as CST? Because if you observe strain displacement relation matrix, which basically correlates strain with displacements, okay, is a constant matrix. Okay, so this is going to give me one matrix which doesn't have any variable in it. Okay, which doesn't have any variable in it. When I partially differentiate all its shape functions, I eventually get direct values of betas and gammas. Okay, betas and gammas are constants. Okay, and that is the reason why strain becomes constant. Okay, strain becomes constant. So strain eventually becomes a constant multiplied by primary variable. A constant multiplied by primary variable, and that means it will be a constant at all stages, and that is the reason why it is also called as constant strain triangle, or CST, and that is the reason this 3-noded triangular element can also be called as constant strain triangle element, or in short CST element. And in exam very oftenly they ask you, say a CST element with so and so coordinates is having these displacement values, identify the stresses and strains. Okay, so don't get confused. The CST element is nothing but the 3-noded triangular element that we have seen just now. And CST, why it is called CST? Because the strain, whatever calculation we have done for strain, that strain is nothing but constant multiplied by primary variable, which eventually remains as constant, and that is the reason why this constant strain triangle element is the name given. Okay, so when we continue our discussion, so once we find out the strain matrix, okay, once we find out the strain matrix, then we can go on and try to find out the element stiffness matrix. Okay, element stiffness matrix. So that element stiffness matrix is it is already known to us. Okay, we have also seen this in beam analysis. Okay, the element stiffness matrix is given by the integration over the volume transpose of my strain displacement multiplied by my stress strain matrix multiplied by my strain displacement matrix and integrated over the volume. Okay, so when I write it at an elemental level, okay, getting rid of the volume term, okay, so volume I will consider as thickness multiplied by area, that is the volume. Okay, so I have transpose of my strain displacement multiplied by the stress strain matrix D multiplied by B, okay, that is my strain displacement multiplied by T and A, okay, that will give me eventually the element stiffness matrix for three noded triangular element or CST element. Okay, now remember what are the orders. So transpose of my strain displacement, the order is 6 by 3. Stress strain matrix is 3 by 3. This is the stress strain matrix from where I am deriving. This is a same plane stress condition. Okay, so on the left hand side I have stress, okay, and on the right hand side I have multiplied by strain. So the matrix which gives me a correlation between stress and strain is called as stress strain matrix. Similarly, the matrix which gives me correlation between strain and displacement is called as strain displacement relation matrix. Okay, so similarly, so this matrix I am utilizing. Okay, so the order is 3 by 3 and then this particular matrix which is strain displacement is order 3 by 6. Okay, so you can do multiplication in any sense. 6 by 3, 3 by 3. So what will remain? 6 by 3 will remain. So 6 by 3 multiplied by 3 by 6. The final order of my stiffness matrix is going to be 6 by 6. Okay, so in this way we have seen the derivation of the strain, okay, for the three noded triangular element, and eventually we found out that the strain remains constant, and that is the reason why it is also called as constant strain triangle element or CST element. And we have just gone ahead and found out the element stiffness matrix using the known formula. This is the formula. So transpose of my strain displacement multiplied by stress strain multiplied by strain displacement multiplied by the volume term will give me element stiffness matrix for CST element or three noded triangular element.